Welcome to Ask and Learn.
Our question is repeat the questions problem from 9 to 57 but replace an isentropic expansion process with a polytropic expansion process with the polytropic exponent n is equals to 1.35. Use variable specific heats. So as we know that we have a compression ratio of 20, thermal efficiency and the mean effective pressure are to be determined. Thermal efficiency and mean effective pressure, that is MEP, are to be determined, and the constant gas constant R is equals to 0.287 kilojoule per kg dot K. That is given in the question. Kilojoule per kg dot K, that is given in the question. This is the P and V diagram. This is the Q input. This is Q out, heat rejected. And the process is polytropic. In the first process, one to two, that is, during this process there is an isentropic compression. Temperature T1 is 293 Kelvin, at which U1 and VR1 is equals to U1 is 209.06 kilojoule per kg and VR1 is 659.2. Now we will calculate the value of VR2, that is equals to V2 over V1 VR1, that is equals to 1 over R VR1. Putting the values, R compression ratio R is equals to 20 given. You will write it here 659.2, that is equals to 32.69, and these are at temperature T2 and H2. T2 is equals to 912.7 Kelvin and H2 is equals to 947.17 kilojoule per kg. During the process 2 to 3, that is P is equals to constant heat addition. P3 V3 divided by T3 is equals to P2 V2 divided by T2. This implies that V3 over V2 is equals to T3 divided by T2. that is equals to 2200 divided by 912.7K. 2.410. At temperature T3, that is 2200 Kelvin, H3 is equals to 2503.2 kilojoule per kg, and U3 is equals to 1872.4 kilojoule per kg. Q input is equals to H3 minus H2, that is equals to 2503.2 minus 947.17. This is equals to 1556.0 kilojoule per kg. During the process 3 to 4, that is polytropic expansion, T4 is equals to T3 into V3 divided by V4 n minus 1, that is equals to T3 2.410 V2 over V4 n minus 1, that is equals to T3 2.410 divided by R divided into power n minus 1, which is equals to 2200 Kelvin, is the value of T3. Compression ratio is 20. This is n minus 1. N minus 1 would be 0.35, and this will turn out to be 1049 Kelvin. Work done from 3 to 4, that is outward work done, is T4 minus T cube 1 minus n, which is equals to 0.287 into 1049 minus 2200 divided by 1 minus 1.35, that is 943.8 kilojoule per kg. At temperature T4, that is 1049 Kelvin, we have U4 is equals to 801.13, and energy balance gives E in input energy minus E out is equals to del E whole system energy. That is, in the process 3 to 4, outward heat minus work done, outward work done, is equals to U4 minus U3 is equals to Q3 out, that is equals to minus W3 3 to 4 outward work minus U4 minus U3. Putting the values over here, we get minus 943.8 minus 801.13 minus 1872.4, 127.5 kilojoule per kg. During the process 4 to 1, it is constant heat rejection Q4 to 1 out is equals to U4 minus U1, that is equals to 801.13 minus 209.06, that is equals to 592.1 kilojoule per kg. So total heat rejected is Q out is equals to Q4 to 1 out, putting the values 127.5 plus 592.1, that is equals to 719.6. And net work outward is equals to Q in minus Q out, which is equals to 1556 minus 719.6 equals to 836.4. 836.4 kilojoule per kg. So thermal efficiency will be equals to W net outward divided by Q in, which is equals to 836.4 divided by 1556, that is equals to 0.5375, which is 53.8%. Now at last we will calculate mean effective pressure. For that we will first write V1 is equals to R P1 divided by P1, which is equals to 0.287 into 293 divided by 95 is equals to 0.8852 meter cube per kg is equals to V maximum, as V minimum is equals to V2 is equals to V max divided by R. So mean effective pressure would be equals to W net out divided by V1 minus V2. That is W net out divided by V1 into 1 minus 1 over R, that is equals to 836.4 divided by 0.8852, 1 minus 1 by 20, that is equals to 995 kilopascal, which is our answer.